Hey guys, it's Mrs. Hinckley. In this lesson, we're going to continue looking at the fundamental theorem of calculus. But first, let's recall that the definite integral is interpreted as area. It's the area of the region bound by the function, the x-axis, x equals a and x equals b. So one thing that we touched on is that areas above the x-axis are positive, but areas below the x-axis are considered negative. So when you're looking at an accumulation of the areas, you really want to subtract any areas below the x-axis because you kind of think of them as negative. So for example, if I were to sketch a curve and I'm integrating this from a to b, I'm looking for the area between x equals a and x equals b bound by the function and the x-axis. The definite integral would just equal the area of the green region, which is positive, plus the negative region, the pink region. In other words, it would be the green minus the pink to give us that total answer for the definite integral. All right, let's take a look at this example where you're evaluating the integral from 0 to 3 of x minus 1. You could use the fundamental theorem of calculus, and you can take the antiderivative here and then plug in 3 and plug in 0 and subtract. But I want you to have an idea of how to do this with the area interpretation as well. So if we sketch out the line x minus 1, and then we look at the regions between 0 and 3, you can see I have one region below the x-axis and one region above the x-axis. So to take the integral from 0 to 1, that's going to end up being a negative answer because it's below the x-axis. So we calculate that area of that little triangle, and it's 1/2 base times height, or 1/2 1 by 1, which is just 1/2. And then the area of that positive region, or the integral from 1 to 3, we would take that triangle, which is a 2 by 2 triangle, and do 1/2 base times height, and we end up getting 2. So to get the total integral from 0 to 3, we simply take that green region, which was 2, and subtract the pink region, which is 1/2. So the grand total is just 2 minus 1/2, or 1/2. All right, so the fundamental theorem of calculus has two main conclusions. If f is a continuous function on a closed interval from a to b, we know these two things are true. And just for the record, technically the first part of the fundamental theorem is the second thing that we're discussing, and part 2 of the fundamental theorem is the first idea that we have been reviewing. So just to go over the part 2 that we've already learned, you know that if you have the definite integral from a to b, you can simply take the antiderivative and evaluate that by plugging in the top limit b, subtracting with the bottom limit a, and that difference will give you the definite integral. Okay, so now part 1 of the fundamental theorem of calculus, which is the second piece that we're going to be discussing, states if my function is defined by the integral from a to x of f, then the derivative of that function is simply f. Think about it this way. The derivative of an antiderivative just gives me the function. So I just want to kind of help you out with these different letters here from this part of the fundamental theorem. The a that you see, that's just a fixed constant. The x is the actual variable that we're working with, and then the t is just what we would call a dummy variable. So let's see an example of using this part of the fundamental theorem of calculus. If you're given y equals the integral from 3 to x of the square root of 4t squared minus t, and we want to find the derivative of that function, it's pretty simple. You just replace the t's with an x, and that's it. That is y prime. But what if our function is defined by y equals the integral from 3 to x squared? So notice it's not just an x, it's an actual function of x. So in this situation, you're going to want to actually use the chain rule to find y prime. So in general, if my y looks like this, an integral from a constant to a function of g, y prime can be found by still using that same technique where you replace all of the t's with that upper limit f of x, but instead of just leaving the f of x there, you have to actually multiply by the derivative of f of x when you're done because you have to use chain rule. So in this example, if I want to find y prime, I'm just going to replace all of the t's here for that function with that upper limit, x squared. But since it's not just x, in order to take the derivative properly, we have to then multiply by the derivative of x squared, which is 2x. So then our final answer is 2x root 4x to the fourth minus x squared. All right, let's move on. So here is an AP style problem using the second part of the fundamental theorem of calculus. Well, technically the first part of the theorem. But if we have this function capital G defined by the integral from 0 to x of f, and f is this function graphed below. So I'm going to label this f so you know that that's what we're looking at in the picture is f. So in the first part of this problem, they're asking you to calculate g prime of 3 and g prime of 12, which means we have to understand what the derivative of this function is. Well, using the fundamental theorem of calculus, we know that g prime is simply equal to f of x, according to the fundamental theorem. So when I'm talking about g prime, what I'm really talking about is f. So to answer these questions, it's really pretty simple. What is f of 3? Look at the picture. F of 3 is 5. So the answer to that first part is g prime of 3 is equal to 5. That's it. So we'll do the same for g prime of 12. G prime meaning f of 12 is 0. Okay, so for part B, they're not asking about the derivative, they're asking about g. So for g, I'm going to evaluate the integral from 0 to 3, and then the integral from 0 to 12. So what does that mean? I don't have a function to actually take the antiderivative of. We have to remember that the interpretation for the definite integral would be the area between the curve and the x-axis. So I'm going to start with g of 3. G of 3 would simply be the integral from 0 to 3 of our function f. So we're going to go ahead and look for the area under the curve from 0 to 3. So the area from 0 to 3 is this trapezoid. So recall the formula for area of a trapezoid is 1/2 base 1 plus base 2 times the height. So this area would equal 1/2 2 plus 5, which is 7, times the height of the trapezoid, which is technically this perpendicular piece here, which is 3. So we get 21/2 or 10.5. So that would be g of 3. All right, next, to interpret g of 12, we have to think about this as separate areas. So we're looking at this whole area with the trapezoid, including this area of the triangle. So that would be our integral from 0 to 8. But then we have to take into account this triangle here from 8 to 12. Notice this is a region below the x-axis, so that means that's going to be negative. We're going to subtract that from this positive area to get our total. We knew the area of the green region was 10.5, and the area of the blue triangle here is just 1/2 5 by 5, so that's going to be 12.5. And then the area of that pink triangle region is going to be 1/2 4 by 3, so it's going to be half of 12, or just 6. So we're going to be subtracting that 6 from the quantity 10.5 plus 12.5. So altogether, this definite integral equals 17. So g of 12 is just 17. Okay, now let's answer question C. It's asking what intervals is g prime increasing? Well, remember, g prime is just the function f. So essentially it's asking you, where is the function f increasing? Well, this is pretty simple. Just take a look at the graph and identify where this function that is graphed is increasing. And this happens from 0 to 3, and then again from 10 to 12. Okay, question D is asking what intervals is g increasing? Not g prime, but g. So g is represented by these areas, which means we're essentially just looking for where f is positive, is increasing. Let's take a look at part D. It's asking over what intervals is g increasing, not g prime. So remember, g represents all these areas here. So if we want to know where g is increasing, we're really just looking for where its derivative is positive. So when you're looking for where a function is increasing, you're looking for where the derivative is positive. So the derivative, again, represents f. So we're essentially just looking for where f is positive. You can also look at it as where are the areas positive or above the x-axis. So this occurs from 0 until we get to 8. That's where we have a positive derivative. In other words, g would be increasing. So the answer to part D would be from 0 to 8. All right, guys, so that's it for this lesson on definite integrals and using the fundamental theorem of calculus. I'll see you next time. Thanks.